turn off Elliot. Swing the microphone in my direction. Can you hear me? Thanks, Lolly. All right, where's the chat? All right, so my chat is open. We're at 12. We're halfway there, but I'm going to get started. It's 10:30. Happy Tuesday the 13th, everyone. We are on the back stretch of the semester. We've made it halfway. Congratulations, everybody. Let me get my iPad out there. Ah, good. It's working. Oh, those are supposed to go off. All right. Every time I share something, the configuration of Zoom changes. All right, so I've got the iPad displayed here, and I've got some announcements. I continue to grade. I know I'm behind. I apologize. I feel terrible about it, but I'm continue to work. Thanks for turning in your quiz work last week. There's some screencasts out there for you to view. The last time I looked, and I think the screencasts are published on YouTube, so I get to track how many people watch it. And I think there's some people that still need to watch the screencasts from last week. So make sure you watch those. Those have material in there that I need you to understand. And I'll ask if anybody has any questions on the screencasts before we get rocking and rolling today. I've got half of a homework assignment written. It concerns what I talked about last time, the binomial random variable, the exponential random variable, mean, variance, standard deviation. And today I'm going to talk about continuous random variables. So I'm going to add some problems on continuous random variables. I don't know how far I'm going to get. So I'm just going to wait to add those problems to see how far we get. And then today we are making, well, not today. Today I think is going to be our last day of probability theory. There might be some topics that we need to go and pick up on a case-by-case basis. But I think we've covered everything that we need to cover. So next time we're going to start working out of the statistics text. So I'm going to write down here next time. So this is for next time. I want you to read chapter 1 of Navidi. It's not a long chapter, and it's kind of a high level thing, high level overview of how we look at data. And we've talked about a bunch of that this semester already when we've talked about looking at probability distributions. So I think it's going to be an easy read for you, but come with questions if you have them. I want you to review chapter 2. Just look over it. Chapter 2 is on probability. And we've talked about just about everything that's in there. But I want you to know what Navidi talks about because what the author puts in that chapter is likely what the author is going to use later. So you'll get a sense of what sort of things are going to come back and be used by just reviewing chapter 2. And again, come with questions if you want some clarification. And the next thing that I want you to read is chapter 3. I'll write out the word. Sections 1 and 2. Okay, this is where real statistics is going to start. This is where conversations about error happen. So read chapter 3, sections 1 and 2, and read those closely. I think that's going to be new. It's going to have new vocabulary. When you read this, you'll see we're really going to be taking a hard pivot away from probability and toward statistics. And that's the idea that so let me write down a wait. Statistics differs from probability in that, probability, it's sort of the theory of random processes. And you start out with an understanding of the pattern, and then you make statements from there. Statistics is sort of the opposite. You've got phenomena out there that you want to understand, and you begin by making measurements, okay, of a phenomena. And this is often in the form of a sample. That is, you can't measure everything. You can only measure part of it. And so you get what's called a sample. And then you try to make predictions about the phenomena from that sample. Okay, and this is often called inference. So we're going to talk about what some people call inferential statistics. We're going to work our way up to that. And it's going to rely on what we're learning about random variables and how to measure probabilities, because we're going to be talking about probabilistic phenomena. And so the language we use to talk about those phenomena is really informed by the language we've been studying so far this semester. And ideally, what will happen is that when we make measurements, we'll say, the thing we're making measurements follows the pattern of an exponential random variable. And that allows us to make predictions with confidence. So that's kind of what we're going to start doing. So I'm going to start the lecture today saying a couple more things about discrete random variables, just reminding us some things that we've already calculated. And then I'm going to start talking about continuous random variables. We've already talked a little bit about them. So you've kind of been oriented to them a little bit, but I'm going to talk about some special types of continuous random variables, just like the binomial is a special type of discrete random variable. The exponential is a special type of discrete random variable. I'm going to talk about 2 or 3 special types of continuous random variables. All right, before I get into that, does anybody have any questions on, for example, the screencast or on anything that we've talked about so far this semester? If you do, vocalize it or throw it into chat.
So to clarify, when you say review chapter 3 and read section 3, 1, and 2, that's also of Navidi?
Those are also of Navidi. So just so we're clear, I don't want you to read the whole chapter 3, just chapters 1 and 2, or sections 1 and 2 of chapter 3. Okay, but yeah, all the reading that we're going to do from this point on, you can assume it's going to be from the Navidi textbook. Good question. Any other questions? I'm looking for my chat window and I don't see it. There it is. I see nothing in chat. Any questions at all about anything?
Did we cover exponential random variables last week?
Oh, good catch, man. No, I mix these up in my brain. It's the Poisson. And I always confuse
that makes more sense.
Yeah, exponential with Poisson, because the Poisson's probability mass function has an exponential in it, right? It's got an exponential equation in it. Yeah, thanks for the catch. Today, I will talk about a continuous random variable that's called an exponential random variable. So that explains a little bit more the depth of my confusion with vocabulary. And I guess it's worth saying, yeah, that vocabulary is becoming very involved now. We've got lots of things that we're keeping track of. So it'd be good to spend time making sure that you're straight on lots of vocabulary. Okay, so just a quick review of some things we talked about discrete random variables. Discrete random variables have these, sometimes we call them probability distributions. The book likes to call them probability mass functions. And we abbreviate those as PMF. We've been using the term probability distribution function sometimes. We abbreviate that as PDF. I really feel like they're interchangeable, these terms, but let's use probability mass functions for discrete random variables, and then we'll use probability distributions for continuous random variables. I think that's a convention that it'd probably be good for us to fall into. Probability mass functions. I'm going to abuse this. If you represent your sample space on a horizontal axis, right? Since it's discrete, the elements of your probability or the elements of your sample space are kind of dispersed along that axis. But what we're interested in a lot of times is, well, what's interesting to us and has value to us is understanding what shape the probability mass function has. Yeah.
Is the probability density function, is that rho?
The probability density function, is that rho?
Sorry.
So a lot of times we've used little p of x to denote the probability mass function. And oftentimes, if we use capital P to denote the probability, this is how the probability mass function is defined. So the value of your probability mass function equals the probability that your random variable equals the input. Is that good, Patrick?
Yeah, that makes sense. Thanks.
Okay. So back here to the picture I'm drawing, a probability mass function, right? We represent discrete random variables as bar graphs. And so our probability mass function might look like this, and the red dotted line kind of shows an overall shape of the graph. So there's an idea of measuring a probability mass function and finding its center. What words do we associate with the center of a probability mass function? Anybody remember?
Mean, mode, median.
Yeah.
Yeah, depending on what we mean by center.
Yeah, depending on what we mean by center. And right now, the only thing we've really talked about is mean. So median and mode are things that will come out of statistics when we talk about samples. But right now, mean is, of those three words, mean is the one that we've used. Right? And we've used the Greek letter mu, the lowercase letter mu, mu, to denote that. There's another, and sometimes if we have a random variable x, we'll put the symbol as a subscript on that mu. There's another term we use to describe this center or this mean. Anybody remember what that is?
Expected value.
Very good, Edward. Expected value. And we use this fancy symbol with a bold E. This is a little bit messy. Let's clean that up. Oh, I don't want to know that. Okay, so the mean and the expected value, they're the same thing. They tell us where the center of the probability mass function is. And one way to think of that is that there's an equal amount of weight to the left and the right of the mean, if you think about the area under the graph as being the weight or something. But that's hard to do with a bar graph. Yeah, you'll see more about why I draw that parallel in a minute. So there's another measurement we use that we find it interesting and valuable when we talk about probabilities and random variables. It talks about the spread, how the values spread out. What is the technical term we use for measuring the spread or the dispersion of a random variable?
Variance.
Variance and its square root standard deviation.
Right, those are the two ways. Variance. Okay. And I denote it with this term var x, but the book has liked to use this symbol, sigma sub xx or squared. And then there's the standard deviation. Sigma sub x, okay, which is the square root of variance. Okay. We should prefer, I think this is a value judgment, but I'm going to make the value judgment. We should prefer standard deviation because standard deviation will have the same unit as the random variable x. The variance, oops, I did that wrong. 1/2 power. The variance has unit squared as its unit. So it doesn't agree with the units on the original random variable. Okay, good. So last kind of warm-up thing. There are three random variables that we've talked about, three discrete random variables that we've talked about that have merit, they earn a name. It's the Bernoulli, the binomial, and the Poisson. Okay. And each of these have parameters that we associate with them. Okay, so the Bernoulli and the binomial have a parameter p, and that's the probability of a success. So a Bernoulli random variable measures sort of the success of a, what do we call it? A binary random variable, has two outcomes. I can't read my writing. Probability of success. In the binomial, the binomial random variable represents a repeated trial or a repeated Bernoulli trial. So you've got a Bernoulli trial, so the probability is the p is the same, and n is the number of trials. Okay, so 2 parameters. And then a Poisson has a parameter called lambda. Just one parameter. And the only thing we really know about the Poisson random variable right now is that it's got an easier probability of mass function to talk about, and the probability of mass function approximates the binomial probability mass function in certain situations. So let's just review what we know about the mean and standard deviation of each of these three random variables. Okay, so we're gonna just make a chart. So if you want to play a game, you can fill in this chart before me. So Oh, yeah, and then we'll do standard deviation over here too. So if I've written down these discrete random variables, and I've written down the parameters. Oh, I guess one other thing that distinguishes the binomial from the Poisson that's good to keep in mind is the binomial random variable is a finite discrete random variable. Its sample space is finite, but the Poisson has an infinite sample space, so it's an infinite discrete random variable. But nonetheless, the Poisson can be used to approximate the binomial in certain circumstances. Okay, random variables, their parameters. We can express these descriptive, I'll call them statistics, for these random variables in terms of their parameters. And so I'm going to start with the easiest one. The Poisson is the easiest one. The Poisson with parameter lambda. The mean, the expected value, is also lambda, and the variance is also lambda. And if you know the variance, then you know that the standard deviation is the square root of the variance. So that's an easy one to fill in. Okay, so that means that if you've got an exponential, or sorry, a Poisson random variable, its mean, its middle, its center is going to be at about lambda, and its spread is going to be about lambda. A Bernoulli random variable, the expectation is going to be p. Okay, that's if you say a success is 0. No, a success is 1 and a failure is 0. If you give the outcomes those numerical values, then the expected value is p. The variance is p times 1 minus p. So that's the probability of success times the probability of failure. And then the standard deviation is the obvious. And then for the binomial random variable, the mean is n times p. The variance is n times p times 1 minus p. And the standard deviation is, of course, the square root. Okay. So these are things to keep in mind, to remember, partly because these random variables will rear their heads in applications, but there's also some theorems that are going to come up that I'll mention next time that involve or that bring the binomial random variable back to the front and lets it have a center stage to talk about some phenomena involving statistics. Okay, so I want you to be able to calculate the mean and the variance for various random variables. So on the one hand, it's good to be able to calculate. It's a good skill to have. On the other hand, it's good to know this table because maybe that will speed things up. But remember that the expected value, or the mean, that's the sum, or that's the weighted average of the things in the sample space. And the variance, okay, it turns out the variance is the expected value of x minus mu squared. And I'll talk a little bit about what this means today. But it's the sum of the squared distance from the outcome, or between the outcome and the mean, times the probability. And then there's a cool algebraic formula that says you can rewrite this as the expected value of this new random variable called x squared minus the expected value of x. And that's going to look familiar to you because I know you watched my screencast on the Poisson random variable and the binomial random variable, where I used these this formulation for the variance to calculate the variance of these random variables. Okay, that is to say, this is a convenience for calculation. This is the definition. This is a convenience calculation. And it's kind of a neat pattern. It's got those squares there inside and outside. But I'll explain what this means in a second. We haven't talked about this. So I'll explain what this means, and then it'll explain what that means.
So you said the left-hand side is the definition?
This is the definition of variance.
Okay, thanks.
Yeah, this is the result of a theorem or a proposition, and it's a calculation convenience is what I called it. Okay, so let me explain what I mean by that. Notation. So if we've got a random variable and then we do weird things to it, like I subtract a constant from it, or I square it, or I could multiply it by 2. These are all random variables. Okay, they're all new random variables. They're different from X. So let me tell you what they are. Let me tell you how to think about these. But they're all new random variables with sample space derived from omega. So if X is a random variable with sample space omega, then all these new random variables have sample spaces that are derived from omega. Okay. And the question is, if we know the probability mass function for X, what is the probability mass function for the new random variable? Because that probability mass function is something that we need to, if we want to calculate the expected value of these new random variables. So let me just generalize this for a second. If X is a random variable, and if G is a real valued function, and I believe it's a real valued function from the sample space of X to R. So let me just throw this in here. Then we can say G of X is a random variable. And then our question is, what is the probability mass function of the new random variable? And I'll just point out the reason that we want to know this, the reason this question is interesting is, and I'm going to just swipe back. I'll double check to make sure. Yeah, I'm recording. Here's an instance where we start with a random variable X, and I create a new one by subtracting mu from the random variable and then squaring what I get, squaring that difference. So what I'm talking about in generalities on the next slide, it has immediate applications for this because this is the definition, okay? And right here, I started with a random variable X. Now I'm talking about a random variable X squared. All right. So the idea is going to be this. If omega is your sample space for X, then the sample space for g of x is going to be the set of elements where g is applied to them. So that's pretty simple. Okay. And the idea also is that the probability that g of x equals xi is going to be equal to the probability that x equals xi. So this is the answer to what's the probability of mass function of g of x. Well, the probability of mass function of g of x is right here. This is the definition. And
I'm confused. I would expect that the definition would give us that the probability of g of xi would equal the given probability. What happened to the g of x on the xi?
oh no, that's good point, good catch. So you're saying, oops. So you're saying right here, yeah, because xi isn't necessarily in the sample space. Yep, a g should go there. Thanks, Patrick.
And I'm also confused. It looks like here you're assuming that the function is 1-to-1. Or am I misunderstanding?
I'm thinking. So what I hear you saying is that if all of the xi's are different in omega x, you're saying, don't we want all these g's to be different? That's what it would mean to be 1-to-1. But that doesn't need to be true. That's not a requirement. All you need to have is this g is be a real valued function. And if g is a constant function and all these go to the same place, that's still okay.
Okay, I that just seems like it would give us, if g was a constant function, it seems like it would give us a probability other than 1 that g would have that g of x would have that constant value, or am I just misunderstanding that?
Well, the ideas might need to be teased out a little bit. So for example, if there's more than one xi that goes to here, that goes to the same value here, then you might need to be adding some things on this side. But the key idea, just the main idea behind finding the probability mass function of this new random variable is kind of this idea that your original probability mass function, right? This is the definition of piece of xi, your original probability mass function. It informs directly your new probability mass function.
Okay, that makes sense.
And you're so for all practical purposes, for everything that we're going to do in this class, this g function is going to be 1-to-1. Okay, it's absolutely going to be. I'm stopping. 99% of the time, 90% of the time, it's going to be 1-to-1. Okay, so it's not going to be a huge issue. I'm pausing here because as I go back, this is an example of a g that's not 1-to-1 because of the symmetry of squaring, if you think about a parabola. But yeah, I can show you what happens with that and why we're not too worried about it. But the important idea here is this idea. This idea is exact when g is 1-to-1. If it's not 1-to-1, then it's a little more complicated. So maybe I'll make that caveat. This is precisely true when g is 1-to-1. And I'll just leave it there. So let's just work an example of how this might work. So let's let X be denote the number of heads that come up when you flip a coin 2 times. So that means this, our sample space is 0, 1, or 2. You could have 0 heads, you could get 1 heads, or you could get 2. So let's consider the random variable x squared. So that sample space, you just square the elements of the previous sample space, right? In this case, g is the squaring function. So 0 squared is 0, 1 squared is 1, 2 squared is 4. So that's where my new sample space comes from. And what's my probability of mass function? So let's, for simplicity, let's denote x squared by the symbol y. So we can say, what's the probability my random variable y equals 0? Well, that 0 comes from the 0 in omega. So this 0 comes from that 0. So the probability this 0 can only happen when that 0 happens. So the probability that y equals 0 is the probability that x equals 0. And we know the probability that x equals 0 is 1/4. Similarly, the probability that y equals 1, because the 1 only happens when you have a 1 from x. So the probability y equals 1 is the probability x equals 1, and that's 1/2. And then the probability that y equals 4, well, the 4 only comes from x being 2. So the probability that 4 happens is 1/4. So here's the probability of mass function for the new random variable. Now, if we had in our sample space somehow a -1, so there were 2 things that map to 1. So this is getting to Patrick's question about one-to-oneness. It's this case where there could be more than one way that y could happen, or that y could be equal to 1. We'd say the probability x equals 1, or the x equals 1 or -1, for example. And so you have to calculate that probability. And so that would change that number in that new distribution. So that's the kind of logic that would happen in the case you have a g that's not 1-to-1. So let's just do an exercise in computing means. So the mean of my random variable x, that's the sum, that's the weighted sum of the outcomes. So my outcome 0, it occurs 1/4 of the time. My outcome 1 occurs half the time. And the outcome 2 occurs 1/4 of the time. So you add those up, we get a half plus a half, we get a 1. So our mean for this random variable is 1. What's the mean for the random variable x squared, which we called y here? Well, same thing, weighted average of the outcomes. So one of the outcomes is 0, that happens 1/4 of the time. One outcome is 1, that happens 1/2 of the time. And one outcome is 4, that happens 1/4 of the time. And so you add those up and you get 3 halves. So you can see changing the random variable is going to change just the shape, the center of the random variable. It's kind of shifted our center up, because this 4 is a lot bigger than 2. So by moving it out this way, it's also moved the mean up from 1. So let me give you a proposition. If x is a random variable, a discrete random variable, actually, well, yeah. with probability mass function P of X. And if G is a real valued function on the sample space of X, then this new random variable G of X, its expected value is the weighted value of its outcomes. Okay. So here you're taking X's out of the sample space, but you only need to consider those where the product of those two things is positive. And in my opinion, so the book I got this out of has this condition. Don't worry about this, because the only thing that can happen, the only other thing that can happen, either they're positive or they're equal to 0. And if they're equal to 0, then they take care of themselves, right? You're just having a summand of 0. Okay. So the operative part of this definition is that. And just so you're clear about
why can't they be negative?
Why can't? Oh, yeah, I guess you're right, because G could be negative. G could be a negative number. But that doesn't matter. Yeah, I don't agree with this. You can have negative expected values. That's not a problem. I don't know why the book was talking about that. So take this as the definition. It's okay for it to be negative. So just compare this to the expected value of a random variable X. That's the sum as X comes out of the sample space of X times P of X. So once you see that the differences in the formula are minor, and in fact, if you're taking G of your random variable, then you just put the G there. That makes this formulation easy to memorize. Okay, or easy to remember. So when you look at this alternate formulation of the variance as the expected value of EX squared minus the expected value of X squared, then this summation here is pretty easy. Just the sum of X squared times P of X. And then this thing down in the end is the sum of X P of X squared. Okay. Yeah. So, right, and this is I'm going to just write this over here. This is another proposition, and it's in our textbook. It's proved. It's just algebra. It's an easy proof just using algebra. So I'm not going to spend time doing it. Yeah. Also, one other closing comment. This proposition here, if X is a discrete, so it assumes X is a discrete random variable. Why? Because this is the formula for an expected value of a discrete random variable. If I change discrete to continuous, the result still holds so long as I put here the formula for the expected value of a continuous random variable. That is to say, this idea extends to continuous random variables just so long as you change the formula to be correct. Okay. That is, where there's an X in the formula for continuous random variables, you put a G of X instead. But I'll talk about that next. I'm going to say something about continuous random variables. Okay, so this concludes the comments that I want to make about combinations of random variables. I'll just close by showing you one way that this immediately connects to stuff that we already talked about. Say if X sub I is a Bernoulli trial, like flipping a coin, then x1 plus x2 plus x3 plus x4. This is a binomial. Say that's a Bernoulli trial with parameter p. Then you add these 4 random variables, each of them flipping a coin, is a binomial random variable with parameters p and n equals 4. This is how you would represent a trial of 4 Bernoulli experiments, okay, as the sum of 4 random variables. Okay. And then if you were to calculate the expected value of these 4, you'd get 4 times p. And so if in general you want to calculate the expected value of a Bernoulli, a binomial NP, that's the same thing as calculating the expected value of n Bernoulli trials with parameter p. Which is that. And there's another proposition. Watch this. How many in the either gallery or the chat, how many people here have taken linear algebra? Anybody here taken linear algebra yet? I don't remember what class it is. Some of you taking it now, Patrick? It is the coolest class. If you haven't taken it yet, it's the coolest class. If you've taken it, I'm gonna state this proposition, you're gonna go. If you're really nerdy, you're gonna go, hey, that's cool. If you haven't taken linear algebra, you're gonna say, oh, okay, cool, Miller. So the proposition says this: if alpha and beta are real numbers, and if x is a random variable, then if you create the new random variable, that's alpha times x plus a constant, and you want to compute its expected value, the expected value is alpha times the expected value of x plus beta. So this means that the expected value is a linear operator on random variables, which is pretty cool because my next step here in my calculation lets me bring this n out. And lets me calculate that the expected value of a binomial NP random variable is n times p, where p is the probability of success. So anyway, expected values, super cool. A lot of great linear algebra that can be done with expected values, and we're not going to really do any. But from a linear algebra perspective, this is kind of a cool proposition. But from a computational perspective, it's also a cool proposition. Right.
I don't think we defined this a function of more than one random variable.
There is only one random variable here.
I think I was just slow on the draw, but it seems like to get from the second line on the left-hand side to the first line to the second line.
Yeah, this
you have to add up. Yeah.
Yeah, but these are just copies of themselves. They're all just Bernoulli trials with probability p. So really, this is a definition of what it means to be n times x. So the subscript, Patrick, you're right. It's distracting. It makes you think that they're all different, but it really is meant to convey that it's a trial. You're doing something n times as opposed to a single Bernoulli experiment. That's all.
Oh, so it doesn't matter that they're not correlated because we just want the expected value. Is that what's going on?
We just want the expected value. We want all of these to be independent. Yeah. So maybe I could have made a better choice with my notation, but yeah, it's meant that you have n Bernoulli trial. I mean, that's what a binomial random variable is. So hope that helps. So I've got, how much time? I've got 25 minutes left. So let me tell you about continuous random variables. Oh, where it goes? Here we go. So the first thing I want to say about continuous random variables is I wrote a handout quite some time ago on visualizing random variables, and it talked about bar graphs and histograms. And when we have a continuous random variable, we use histograms. Those are like bar charts, except the bars are adjacent to one another when we draw them. In that handout, I start developing one of the big differences between probability mass functions and probability distribution functions. And I'll just reprise it here quickly. But if you haven't read that handout, if you don't remember reading that handout, it's on the Canvas site. Go grab it and read it, and pay special attention now at this point in the course. Pay special attention to the last couple pages, because what I'm developing in the last couple pages is really important right now. So if X is a continuous random variable, this means omega is effectively a subinterval of the real line, right? So it means it could be a closed and bounded subinterval, or it could be open on either or both ends, or it could be a doubly infinite interval. Or it could be a union of intervals. What's important is that it's a continuum. Okay. What's important is that it's uncountably infinite. So what that means is summations over omega do not make sense. Okay. Summations only make sense with finite sets or countably infinite sets. They just don't work for uncountably infinite sets. So for the purposes of for the rest of the course, let's just assume that omega is some closed interval of real numbers. If we need to make it more sophisticated later down the road, we can, but for the purposes of just learning about continuous random variables, we're going to assume that omega is some finite interval like this, okay? Or interval of finite length. So X is the random variable. It turns out that if you pick, so let me choose any X in omega, so choose any number. It turns out the probability that our random variable equals that X is 0. So this is very different from the discrete random variables, where the probabilities that our random variables realize some outcome is generally not 0. You know it's always going to be positive, or at least, yeah, non-negative. But here in the continuous case, this idea rules, this idea reigns, okay? So we have to think about probability distribution functions differently. okay, than from probability mass functions. And what I develop in this handout is this idea that we no longer talk about probability of equaling. We don't talk about the probability that X is something. We talk about the probability X is in something. Okay, the probability X is in some interval AB. Okay, the probability X is between alpha and beta. So our probability mass function has this form, or sorry, our probability distribution function has this form. So this is new and different with continuous random variables. So let me so a probability distribution okay, it's a function from our sample space to R that has the following characteristics. And so the first one is going to be very familiar. And you're going to look at me and say, Miller, didn't you just tell me it always equals 0? And yeah, you're right. I said it always equals 0 for any one point. It always equals 0. But here I'm making just a statement about the probability distribution function. And like, think of this graph. The graph of the probability distribution function is always above the x-axis. That's all I want to tell you here. Okay. Because this isn't the statement about the I'll get to where we want us to go. The second property is this. So remember, for a discrete random variable, we said the sum of all the probabilities is 1. And I just made the point that this doesn't push through to continuous random variables because we can't do sums over uncountably infinite sets. So what happens is that we end up taking intervals. So the integral from minus infinity to infinity of our probability mass function is 1. So the upshot is that if I want to know what the probability is, that my random variable has a value between alpha and beta, that equals the integral from alpha to beta of my probability distribution. Okay. So this is the new idea. And we now start talking about the probability that a random variable falls in an interval. Okay. And this is also suggestive of how you build a histogram. So for what that's worth. So if that is suggestive of the width of the base of a bar in a histogram, then the right-hand side is suggestive of an area. So in the context of continuous random variables, we have this probability distribution function that has this sad property that the probability that our outcome is exactly one specific number is 0. So what we do is we define another thing called a cumulative distribution function. Sometimes denoted CDF. And so, so let's let X be some number in our sample space. We can define our cumulative distribution function, capital F of X. It's defined to be the probability that my random variable takes on a value that's less than or equal to X. So if we want to calculate that, that's the integral from minus infinity to x of the probability distribution. Okay. So this is the basic language that we use when we talk about continuous random variables. I'll just repeat. Talking about the probabilities of our random variable falling within an interval. We use an integral this way. And then we have this new idea of a cumulative distribution function that's defined using one of these inequalities. It's worth noting that the probability that x, is between alpha and beta, that's the value of the cumulative distribution function of beta minus the cumulative distribution function of alpha. So the cumulative distribution function is really important to us for making calculations. Okay, if you didn't read that handout or don't remember reading that handout, this is going to be a little confusing, but that handout really develops the idea of this idea of measuring probabilities in terms of integrals. And with that, we talk about this cumulative distribution function. So let me give you some examples of important and common continuous random variables. And we'll start with the easy one. There's the uniform distribution. So the uniform distribution, if your sample space is the interval from A to B, the uniform distribution has a probability distribution of this form. It has values 1 over B minus A if X is between A and B, and 0 otherwise. So you can see that the B is bigger than A, so my denominator here is a positive number. So this reciprocal is a positive number. So you can see this function, all its values are bigger than or equal to 0. If you plot the graph, graph looks like that. So you got this rectangular area. And if you look, the area under this curve is 1. And so that shows that the integral from minus infinity to infinity of this probability distribution function equals 1. So this indeed satisfies the contribution or the conditions on a probability distribution function. It's the distribution function for the uniform distribution. And the idea is any two intervals in AB of the same length have the same probability of occurring. Okay. So if the probability that A less than or equal to X less than or equal to A plus a fourth, that's the same thing. That has the same probability of occurring as that interval. Okay, because they're the same length. And that probability in both cases is a fourth. So it's that equality of likelihood It's this equality of likelihood that makes this a uniform distribution. We can talk about the mean. So let's do that now in this case. So what's the mean of a continuous random variable? Well, in the discrete case, the mean was the sum of the was the weighted sum of the values. So we go to the continuous case. We're going to change that sum into an integral, and that's it. So that's the definition of the mean of a discrete random variable, or sorry, a continuous random variable. You take the integral. I guess I have to put a dx there. So let's calculate the mean for this uniform distribution. All right, so mu is going to be the integral from minus infinity to infinity of x times p of x dx. But because outside of a and b, my probability function is 0. This product inside here, this function is 0 for x is less than a and x is bigger than b. So my integral becomes the integral from a to b of x times p of x. And then what I'm going to do next, giving you time to catch up, I'm going to p of x here is the constant 1 over b minus a on the interval that we're integrating over. So I'm going to just substitute that in there. So let me swipe. I'm going to do that. So now I'm just going to do some calc 1. So I'll pull that constant out. I'm left with x in the integral. And so I'm going to integrate that. I get 1/2 x squared. So as an antiderivative, so I can use the fundamental theorem of calculus. Let's do that. And b squared minus a squared is a difference of 2 squares. So it factors into b minus a times b plus a. And that b minus a will cancel with that b minus a. And I'm left with 1/2 of b plus a. And that's exactly what you hope we would get. Why? Because here's our probability mass function, our probability distribution. What's the center of this? Well, the center is right here. It's at the midpoint of A to B. Right? And so this is how you find that midpoint. So of course we expect mu to be at the midpoint, and this calculation bears that out. Okay, so that's how we find, right? If the mean is the central tendency of a distribution, we want to make sense that it's at the midpoint, and that's exactly what this computation for the expected value or the mean of this turns out. Okay, let's look at 2 more. I've got a few more minutes, right? I've got 7 more minutes. The most important continuous, random variable that we'll talk about is the normal distribution. A lot of times the random variable is denoted by the capital N. Okay, so that's our random variable. And it has a sample space that's the whole real line. And its probability mass function is given by this formula. So 1 over 2 pi sigma times e to the minus x minus mu quantity squared, and still in the exponent, divided by 2 sigma squared. Okay. So this is the probability mass function. This is the probability distribution. No, yeah, probability distribution for the normal distribution. And you'll notice here there's 2 parameters called mu and sigma. So you would be right to guess that mu is the expected value of the normal distribution, and you would be right to guess that sigma is the standard deviation of the normal distribution. And people generally regard these as parameters. So there are things that you kind of specify in advance. This is a bell curve. If you plot it, I can pull out Wolfram alpha and plot this for you, and you'd see it has a bell shaped, and it's symmetric, and its middle is at mu. And I believe if you check these inflection points right here are where the standard deviations happen. But don't quote me on that. It'd be an interesting thing to check, but I think that's what happens. Yeah, so this normal curve is really important in everything that we'll do this semester. It's kind of a central random variable in all of statistics. And it's the cumulative distribution function for this is going to be really important. But one thing to note is if we're interested in probabilities of our normal distribution falling between alpha and beta, and our probability distribution function is this function I drove right here, it's important for you to notice that the fundamental theorem of calculus does not work to calculate this integral for reasons that we can talk about later. So historically, people have used what are called tables of values to calculate these probabilities. I'll show you how to do that, but for us, we're going to use R and numerical tools to calculate these probabilities. R has a function that will calculate the values for this probability distribution. Will calculate these probabilities for us and probabilities for the cumulative distribution function for the normal distribution. So that's how we'll work with this. All you got to do is tell R what these parameters are and what you want alpha to be or beta to be, and it'll give you a number back with whatever degree of accuracy you want. And so R is going to be our substitute for these tables of values. Again, maybe I'll spend 15 minutes one day telling you how to use the tables. But using the tables really relies on your knowledge of what probability distribution looks like, so you can do this interpretation of the meaning of these things. Okay. But R, and we'll talk about how to do this with R. My last note about the normal distribution, and I've got 2 minutes left, so maybe I'll leave my next distributions for next time. A lot of natural phenomena, they are distributed normally. And that's what a lot of people like to say. So the normal distribution occurs all over the place. And a lot of times people say, if you don't have any other reason to believe otherwise, it's always good to start with the assumption that the phenomena that you're measuring is distributed normally. Okay, that's why this is so important. All right, so I guess what I'm going to leave you with is this. There's 3 other continuous distributions I was going to tell you about. One is the exponential distribution. One is the gamma distribution, and one is the beta distribution. of these, the exponential one is the most useful because this often models waiting times. So I'll definitely talk about that next time. These are probably less necessary. These are probably more of peripheral interest, and I can talk about them when the time if the opportunity arises down the road. So if you're looking around for stuff to read online or in the textbooks, take a look at what folks say about the exponential distribution, as well as the normal and the uniform distribution. It's also worth pointing out that insofar as the variance of a random variable is the expected value of x minus the mean squared, right? You can use the definition that we have of expected value for a continuous random variable to infer the formula for the variance of a continuous random variable. I believe it looks like this. Okay. So next time I'll just make a couple more comments on these continuous distributions and we'll start talking about statistics, right? That should be fun. So I want you to think about data. Is there any data out there in the world that is interesting to you that that you'd like to know more about? Is there any data out there that you think it would be interesting to explore using statistics? Yeah, so we can talk about that more later. So now I'm looking in the chat. Charles, you probably didn't get the page that you wanted to see. You want to tell me which page you wanted to see? That's the first page. That's that page. Okay. All right. With that, I'm done. We're over a little over time. Thanks, everybody. Stay safe, stay well, and I will see you on Wednesday. Thursday. I'm sorry, Thursday.
Thank you.
Hi, Professor. I was gonna ask okay, soon you said.
Yeah. So I don't know if you were there when I said that I was gonna pick a few problems to cover continuous random variables. I've got some for the discrete random variables, but I'll be sending these out soon.
Okay, thank you.
Okay.
Bye.
Yep. Bye-bye.